This video we are going to talk about steady state plug flow reactor. First I will draw a schematic of a simple plug flow reactor. Generally in most texts of reaction engineering you will find the plug flow reactor represented as a tubular reactor like this. It may also be slightly coiled at certain parts like this. So there may be some coiling. Essentially, we have a long tube through which fluid, the reacting fluid, flows from one point to another. Okay, and in a plug flow, the most important thing to note is that the composition of the fluid, and by fluid I mean the reacting fluid, varies from one point to another. Okay, so we do not have uniform composition over here. Now accordingly we set up the balance. Okay, now before I start writing the balance, it is important to note that since the composition of the fluid varies from one point to another, so we have to take the differential element of the entire reactor volume. So if this entire reactor's volume is V, let me write here that the reactor volume is V. So we will take a differential element, let's say this section, let's call it dV, across which we are going to set up the performance equation. Accordingly, that differential expression can be integrated to obtain the entire reactor volume. Okay, now obviously when we are talking about steady state plug flow reactors, we will first talk about the material balance equation from which we will derive the performance equation. Okay, so let us do that. So the material balance equation becomes input equals to output plus disappearance of reactant. Also there is an accumulation term which is equivalent to 0 because this is a steady state flow reactor. So the accumulation term is 0 over here. Okay, now if I consider this tubular structure itself or whether it is coiled, let me just write the notations that we are going to use. So at the inlet we have the concentration Ca0, the molar feed rate Fa0, the conversion Xa0 which is equivalent to 0, and the volumetric feed rate is V0. Okay, so across this differential element at the inlet side we have the molar feed rate as, let's say, Fa. On the other side the molar feed rate becomes Fa plus DFA with a constant conversion within this region as dxa. Okay, so we are taking the differential element within this dv volume. Now at the output point we will have CAF as the final concentration, FAF as the final molar rate, XAF as the final conversion, and small vf as the final volumetric rate. Okay, now we are ready to derive the equation. So in the input side you already have Fa across this differential volume, and at the output point you have Fa plus dfa plus the disappearance term is written as minus Ra multiplied by dV. This is your material balance equation. Now if you want to express dfa using the conversion term, then you can write dfa equals to d of fa0 multiplied by 1 minus xa with respect to the conversion term. So this reduces to minus fa0 dxa simply. Therefore, if you replace this equation over here, then you will get fa0 dxa equals to minus ra dv, where minus ra is the rate equation, right? Now, this is the equation which finally gives you the uh, you know which accounts for the reactant A in the differential section dV. Okay, for the whole reactor you have to simply integrate this. Okay, here this fa0 term is constant, but minus ra will definitely be dependent on the concentration or the conversion of the reactant. Therefore you have to appropriately group these terms and then obtain the integrated form. So for integration, what you would do is integration 0 to v dv by fa0 equals to 0 to xaf dxa by minus ra. Okay, if you solve this for any epsilon a, you will get v by fa0 equals to tau by ca0 equals to 0 to xaf dxa by minus ra. Or you can also write tau equals to v by v0 equals to v ca0 by fa0 equals to ca0 0 to xaf integration dxa by minus ra. Okay, this is for the general case when you can calculate the volumetric ratio if you have a gaseous fluid working in it with variable density. So this becomes the performance equation for the plug flow reactor. Okay, the only difference that you should note numerically is in case of a mixed flow reactor, this minus ra term will remain constant, but in case of a plug flow reactor this becomes a variable and therefore it has to be integrated appropriately. Okay, uh, if you are considering that a partially converted feed has been put into the plug flow reactor and you want a very general expression, then how would you write it? So the general expression looks somewhat like v by fa0 equals to integration xai to xaf dxa by minus ra, where xai is the partial conversion of the feed. Accordingly, tau is equals to ca0 integration xai to xaf dxa by minus ra. Okay, if you have a constant density system, that means epsilon a equals to 0, so this becomes a constant density system. Okay, if you have something like that, then you can directly relate the concentration terms. So you can write xa equals to 1 minus ca by ca0, therefore dxa equals to minus dca by ca0. Okay, and appropriately you plug in this formulation, then you will get the performance equation as v by fa0 equals to tau by ca0 equals to integration 0 to xaf dxa by minus ra equals to minus 1 by ca0 integration Ca0 to CAF dCA by minus RA. Or in terms of tau, you can write tau equals to V by V naught equals to Ca0 0 to XAF integration dxa by minus RA equals to minus integration Ca0 to CAF dCA by minus RA. Okay. Now, if you want to graphically represent these performance equations, how would you interpret them? So, for the graphical interpretation, on your x-axis you would plot the conversion, and on your y-axis you would plot the reciprocal of your rate equation. Then you would have a curve like this, and the area under the curve, this area is equals to V by Fa0 or tau by Ca0. Okay, tau here being the space time. If you have a constant density system, the first figure that I have shown, this is for the general case. Okay, if you have a constant density system, then instead of conversion you can now plot the concentration on the x-axis, and on the y-axis you are going to plot reciprocal of the rate equation. Then you get a curve like this, and area under the curve like so gives area equals to tau, that is Ca0V by Fa0. Okay. Now, like I said, for systems where the density is changing, it is more convenient to use the conversions. But for system where the density remains constant, that is epsilon equals to 0, like this here, epsilon A equals to 0, then you would not have to worry so much that you should use conversions only. You can also go ahead with the concentration directly. But in whatever form you use the performance equation, it is actually the interrelation between the reactor volume, feed rate, rate of reaction, and the extent to which the reaction has occurred. So if one of them can be has to be found, then the other three information can be plugged in. Okay, this ideology becomes the same as for mixed flow reactors. I do have a video on mixed flow reactor. Please go through that for more clearer understanding on mixed flow reactors as well. Now, for any kinetic form, okay, for simple kinetic forms, you simply replace minus RA in the performance equation, and you can derive the final expression. You can use that to calculate the reactor volume that you require for the process. We will understand that through an example. Of course, I will not show you the entire derivation, because the derivation is essentially carried out just by replacing the minus RA term with the actual kinetic expression. Okay, and we are going to use a very simple case to exert and solidify our understanding about this plug flow reactor performance. So let's take this example. This example I have taken up from the Levenspiel book. There are other examples also, but this particular example is good for the subject I'm discussing right now, because it is a design problem. So you have a homogeneous gas phase reaction at hand, and the reaction is 4A gives R plus 6S. Okay, this is your reaction. And the temperature at which it proceeds is 649 degrees Celsius. This is the temperature, the reaction temperature. We have a first order kinetics which is fairly simple, and the kinetics is as minus Ra equals to 10 R inverse of Ca. Okay, the design question for us is size of reactor. Here the reactor type being a steady state plug flow reactor operating at 649 degrees Celsius and 460 kilopascal, that can produce 80% conversion of feed. Also, the feed has 40 moles of pure A per hour. Okay, this is our design question. So since this is a gas phase reaction, obviously we are not going to follow the constant density criteria, because we have not been given any other information that whether the density of the system remains constant or not. So we are just going to proceed with the general case. Okay, now let me draw a schematic of whatever the problem statement is going to discuss. Now before I actually move to the solution, I will request you to pause the video and give this example a try on your own at first, and then proceed to see the solution. So hoping that you have done that, let's now see how we would solve this. First of all, let me draw a tubular plug flow reactor. So at the entrance, it is said that we have 40 moles per hour of A, okay, and the temperature is 649 degrees Celsius, and the partial pressure of A is 460 kilopascal, okay, and at the outlet we want 80% conversion of A, so XA is 0.8. The reaction is known to us, the reaction kinetics is known to us. We need to find the volume or size of the reactor. Essentially this is our problem statement. Now you just go to the performance equation for the general case. So if you see the general case performance equation over here, I'm just going to write this again. V by Fa0 equals to tau by Ca0 equals to 0 to XAF dxa by minus Ra. Okay. Now all you need to do is just plug in the kinetic expression for minus Ra over here, considering a first order irreversible gas phase reaction, and you will get the final expression. Okay, so the final expression should look like this: V equals to Fa0 by Kca0, depending on your rate constant of first order kinetics, multiplied by 1 plus epsilon A ln of 1 by 1 minus XAF minus epsilon A XAF. That is it. Okay, so okay, let me just erase this bracket, right? This is the kind of expression you will get if you put the irreversible gas phase uh, variable density rate equation in place of minus Ra and just solve it numerically. Now all you need to do is simply write the correct values corresponding to each term. So Fa0 is already known to us, that is the molar feed rate, 40 moles per hour of A. K is known to us, the rate kinetic equation shows that the value of K is 10 R inverse. Okay, Ca0 is to be found out. Now, if you remember, towards the very beginning of this lecture series, I have already said that when you are dealing with gases, it is important that you do not directly use the pressure term. You must use the gas law to convert the pressure terms to concentration terms and then use it for further calculations. Otherwise, it will lead to mistakes. So we need to calculate Ca0 using this Pa0 information that we have. So to do that, we can write Ca0 equals to Pa0 by RT, and with appropriate units and the values, you will get that this Ca0 equals to 60 mole per meter cube. Okay. The next thing you need to calculate is epsilon A. This epsilon A is not known. So we'll find epsilon A. How do we do that? We are going to use the information from reaction stoichiometry. The reaction stoichiometry shows 4A gives R plus 6S. So on the reactant side, you have 4 volumes, and on the product side, you have 7 volumes. So 7 minus 4 by 4, that is 0.75. So using the reaction stoichiometry, you have found the volume ratio, and XAF is already given as your target conversion, that is 0.8. Okay, so now if you write all the values appropriately, you will get that the volume of the reactor V is 0.148 meter cube or 148 liters. This is how we use the performance equation calculated across a differential volume of a plug flow reactor to ultimately find the size of the whole reactor. So the key takeaway message is that all you need to do is remember the main expression, that is this, the general performance equation, and then depending on the type of reaction that you have and the kinetics provided to you, you just need to plug in the rate equation and integrate appropriately to get the final integrated format, so that you can obtain the size of the reactor. That is it. Thank you.